Okay, so in this video we're going to discuss some exponential and logarithmic equations. Yeah, let's start off with exponential equations. So an exponential equation is any equation with variables in the exponents, such as e to the 3x plus 9 equals 4, and say the equation 3 to the x equals 81. To solve exponential equation, one particular property from exponential functions is the one-to-one property, and the fact that an exponential function is one-to-one says the following. For any b greater than 0, b is not equal to 0, and algebraic expressions x and y, we have b to x equal to b to the y is equivalent to x equals y. And so that's basically saying the exponential function is one-to-one. The direction going this way is that it's one-to-one, and the direction going this way is that it's a function. Okay, so here's our first equation, and we're going to take advantage of that property. So x here, we're actually solve the equation 2 to the 3x minus 7 equal to 32. And so we're going to use the property going this way. And the reason why we can do that is because 32 can be written as 2 to the power of 5. So 2 to the power of 5 is equal to 32. And so using the property, we could see we have an exponent of 3x minus 7 and an exponent of 5. Since these two expressions are equal, the one-to-one property tells us that 3x minus 7 equals 5, which tells us 3x equals 12 or x equals 4. Okay, and you can plug that into the function to check your answer if you want, or excuse me, plug it into the equation and see that you get a true statement. All right, moving on to the next equation. We have e to the x minus 6, e to the negative x equal to 1. This particular equation isn't as simple as the previous one because we have this constant of 1 here. But what we can notice is that e to the x and negative e to the x happen to be related in the sense that e to the negative x is just 1 over e to the x equal to 1. And so this is just e to the x minus 6 over e to the x equal to 1. And this is what we would call somewhat of a rational equation as well, because we have a fraction. And so I like to build up my fractions so they have a denominator of 1. So I'm going to go ahead and think of this one as 1, this over 1, and the LCD would be e to the x. And so I would have to multiply this fraction by e to the x over e to the x on this side. This already has an e to the x, but this doesn't. So we have e to the x times e to the x here times 1. And then doing so would give me e to the 2x over e to the x minus 6 e to the x equals e to the x over e to the x. And then basically forget about the denominators, because if you multiply through by the LCD, you will get exactly this equation. Okay, so this still is not helpful in the sense that we still have this new constant here, and we're not going to be able to combine it. But if we say subtract off e to the x on both sides, we could get e to the minus 2x minus e to the x. I'm sorry, I don't know where I got that negative exponent there. E to the 2x minus e to the x minus 6 equal to 0. And this one's a little tricky if you don't notice it. It has what we call quadratic form, because if you say do a substitution here, like say let u equal e to the x, then notice u raised to the second power. It's the same thing as e to the x raised to the second power, which is just e to the 2x. And so substituting this, you can see this is exactly u squared. And this here is u minus 6 equal to 0. And it's basically quadratic, which can be solved by factoring. And so if I factor this as u minus 3 times u plus 2 equal to 0, this will give us two solutions. U equals positive 3 and u equals negative 2. And so now substitute back we could see this is e to the x equals 3, e to the x equals negative 2. This first equation here, think base here. And so what's the definition of a logarithm? Well, we could say this is basically log base e of 3 is x. In other words, x equals log e log base e of 3, which is just the natural log of 3. And if you need an approximation to that, it's about approximately 1.10 if you round to say 2 decimal places. The other equation we have, this here has no solution here. And the reason is because an exponential function, like just by itself, e to the x, is never going to be negative, so never negative, right? And therefore it can't be equal to negative 2. And so that gives us no solution there. And so our only solution is basically x equal to natural log of 3. And you can plug that in to check to see that the answer, or you get a true statement. All right, moving on. Sometimes exponential equations and logarithmic equations need to use this property, which is the one-to-one property of logarithmic functions. In other words, log functions are one-to-one. So if you have log base m equals log base b of n, this implies m equals n. And this direction is just that the fact that log is a function. Okay, so let's see how to apply it. So here we don't have logs on either side, but we're going to go this direction because we have our, we could think of this as m and this is n, so we could take log on both sides. And in this case, since we have a base 3 here, I'm just going to say take log base 3 of both sides. And we get log base 3 to the, sorry, keep on writing the 3 there. It should be x there equals log base 3 of 20. All right, so once again, log in the log base 3 and the exponential function 3 to the x, they're inverses of each other, so we just get x out there, right, using one of our rules, or think inverses, and then we just have log base 3. You could also have done just how we solved the equation earlier. What's the definition of a log? Well, the base, so we would have, here's the base, right? So, and this is the exponent, and so we have log base 3 of 20 equals x. Okay, however, log base 3 of 20, if we have a basic scientific calculator, most calculators these days I've seen probably carry base 3 logs now, but before they never used to carry stuff like that. However, we could always use the change of base formula to write this as a log base 10 of 20 over log base 3, or even log ln of 20 divided by ln of 3. In either case, if you need an approximation to this, this would be about 2.73 if you took a calculator and computed those. All right, so basically x is equal to log base 3 of 20, or approximately 2.73. Okay, so here we could also take we have 4 and 3 here. However, when we have equations like this and you don't have a common base, and we have exponents or variables and the exponents on each side in the exponent, it's common to just take either natural log or log on both sides. I'm going to take the natural log on both sides to get ln of 4 to the x plus 3 equals ln of 3 to the negative x, right? Once again, that's just using this property, right? We have m equals n and working our way backwards this way. All right, so then now we could apply, say, the power rule for this equation, right? The exponent comes in front here, and so what do we have when we do that? We get x plus 3, the quantity x plus 3, times ln of 4 equals, well, that whole exponent's going to go to the front there too, so we get negative x ln of 3. And then you have to solve for x. Ln of 3 and ln of 4 are just numbers, so if I distribute, I would have x times ln of 4 plus 3 ln of 4 equals x ln of 3. I'm going to go ahead and remove or subtract ln x minus x ln of 4 on both sides here. And that will give us basically 3 ln of 4 on the left hand side, and on the right hand side we have minus x ln of 3 minus x ln of 4. And then notice each one of these have a minus x in common, so I could factor out a if you want minus x, and what's left behind would be ln of 3 plus ln of 4. And if you like your properties of logarithms, I mean, you don't need to, but since this is a sum of two logarithms of the same base, we could write that as ln of 3 times 4, and that would give us 12. So we have ln x ln of 12 equal to 3 times ln of 4. And I kept on not writing that, so let me write that down. Okay. And then now to solve for x, I'm going to divide by negative ln on x on both sides here. Sorry, negative ln of 12, not x, 12. Okay, and that tells me what x is. So x will equal a negative 3 ln of 4 over ln of 12. Okay, and so if you need a decimal approximation to this value, we could see x is approximately going to be about negative 1.67. Alrighty. So x is equal to exactly that there, or approximately negative 1.67. Alright, let's move over to now talk about logarithmic equations. So a logarithmic equation is any equation with logarithmic functions, such as log base 2 of x equals 4, log x plus log of x plus 3 equal to 5. Those are examples of logarithmic functions. So here we have log base 3 of x equal to negative 2. Once again, we could use this property here, but this time we're going to go this direction. Okay, or maybe not. Let me see. Let me look back. In this case, we're going to use the exponential one. And so in other words, we're going to raise, basically, since you have m or x equals y, right? X equals y, and we're going to raise each side to the power of 3. So you go 3 to the log base 3 of x like this. That has to be equal to 3 to the negative 2. Okay, and the left-hand side, well, we know they're inverses, so that's just x equals 3 to the negative 2. In fact, you could also just use definition as well. Definition of logarithms. Okay, so 3 to the negative 2 is really just x equal to 1/9. Alright, so that's how you solve that one. Here we are going to solve log of x plus log of x plus 3 equal to 1. Okay, so technically you can think of that as in parentheses there. We have a sum to logs, so that means we multiply them. And this is log base 10, by the way. So we have x times x plus 3 equal to 1. And so then we distribute to get x squared plus 3x equal to 1. And then since it's log base 10, you could either use the definition or raise each side and put in the exponent. So we have log 10 to the log x squared plus 3x equal to 10 to the 1 using the exponential property. All right, and then those kind of cancel there, or think inverses. X squared plus 3x equals 10, and then this is just a quadratic where we have x squared plus 3x minus 10 equal to 0. Factoring it, we have x plus 5 times x minus 2 equals 0. And we can see that the first solution would be negative 5, and the second would be x equal to 2. But we have to be careful with logarithms because the log function has a domain x greater than or equal to 0. And so if you plugged in x equal to negative 5, it would make this term log of x undefined. In fact, it also makes that term undefined as well. And so x equal to negative 5 is not part of the solution set, and x equal to 2 will be the only solution there. And you can check by plugging in your values. For instance, let me quickly check for you here. We have log of 2 plus log of 2 plus 3. Does this equal 1? Well, let's see. Log of 2 plus log of 5. Does this equal 1? Well, let's see. So then we know this is a sum of 2 logs. And so we could write log of the product of the arguments, meaning 2 times 5, which gives us 10. And log of 10 is 1. So 1 does equal 1, and that checks. All right, let's move on to the next example. And the final example. So we have ln of 4x plus 6 minus ln of x plus 5 equal to ln of x. So we have a difference of logarithms. So a difference of logarithms we could combine as a quotient of their argument. So we have 4x plus 6 over x plus 5 equals ln of x. Okay, so then ln of 4x plus 6 over x plus 5 and ln of x, right, using the one-to-one property, that just means their arguments must be the same. Okay, so we have that equal to x there. All right, so now the next step is to just solve this equation, and it's a rational equation, so I'm going to think of this over 1 and then multiply top and bottom by whatever I need to so that we get the LCD of x plus 5. All right, so this here we will multiply it by x plus 5, top and bottom. And so on the left-hand side, we don't have to multiply it by anything because it already has that as the denominator. And so we have, on the numerator, when we distribute, we have x squared plus 5x all over x plus 5. Now we could forget about the denominators or multiply through by the LCD, which will cancel the denominators to get 4x plus 6 equals x squared plus 5x. And this is quadratic, so we're going to subtract 4x on both sides to get x squared. Once again, subtracting x on both 4x on both sides, we get x squared plus x. Now we subtract 6 on both sides to get 0 equals x squared plus x minus 6. And this is quadratic, so this would factor as x plus 3 times x minus 2. And the solutions for that equation, or when we use the zero factor property, would give us solutions of -3 and x equals 2. And we have to really examine this closely. -3 here is not going to work. It would make the right side of the equation definitely undefined when you substitute it here. And also when you see -3 plus 5, that's okay. And 4 times -3 is -12, but that would make this here undefined. And so we could see that already x minus 3 is not a solution, but x equal to 2 should be a solution, and we could quickly check that's true. In other words, when you plug in ln of 4 times 2 plus 6 minus ln of 4, sorry, not 4, but 2 plus 5, does that equal ln of 2? All right, so this is ln of 8. 8 plus 6 is 14 minus ln of 7. Once again, does that equal ln of 2? Okay, and so, well, yes, it does, because when you have a difference of logarithms of the same base, and here is base e, we would have ln of 14 over 7, which gives us ln of 2, which sees that you could see that that ln of 2 equals ln of a 2. Okay, and that's how you solve logarithmic and exponential functions. That's it for this video.